We can roughly divide line coding schemes into 5 broad categories, as you can see in this figure, and there are several schemes in each category. We are going to be familiarizing ourselves with some of the schemes like NRZ, AMI, Manchester, De Manchester, MLT3, and so on. First up is unipolar, and since this is unipolar, meaning the polarity is either on one side of the time axis, so it's either above or below. So the first scheme that we are going to look at is unipolar NRZ, and NRZ stands for non-return to zero. Now, the scheme is very simple. So 1 is encoded as positive voltage and 0 is just encoded as negative voltage, okay? And just going to explain the graph a little bit here. So of course we are graphing amplitude versus time. So you have time on the x-axis and amplitude on the y-axis, all right? And then you have bit duration set for each of these bits. So your data is 1 0 1 1 0, and you see these vertical lines. So this is the time duration. So this portion is the time duration for the bit 1, and this portion is the time duration for the bit 0, and this portion is the time duration for bit 1, and so on. So you see that the bit duration for each of the bits is the same. Okay, so like I was saying, that this is a very basic, straightforward encoding scheme. 1 goes on the positive and 0 goes on 0, right? And this is called NRZ because the signal does not return to 0 in the middle of the beat. Okay, so that's basically it. If you are given a data stream and then you have to encode it using unipolar NRZ, you just encode the ones as the positive voltage and the 0 as 0 voltage. Okay, so next up is polar encoding schemes, and I personally find polar encoding schemes to be sexist, and I am not sure if I can encode using polar encoding. So if I make any mistakes, it's not on me. Yeah, I know. In polar schemes, the voltages can be on both sides of the time axis. So suppose this midline over here, this is your time axis. So this axis is your time. Now, the voltages are on both sides of the time axis, okay? For example, the voltage for 0 can be on the positive and the voltage for 1 can be on the negative. All right, so in polar NRZ encoding, we use 2 levels of voltage amplitude. We have 2 versions of polar NRZ. You have NRZ-L and you have NRZ-I. Now, in the first variation, NRZ-L, L over here stands for level. The level of the voltage determines the value of the beat. All right, so the level for 0 would be, all right, let's first mark, this is going to be our 0, this is going to be positive, or you can just call it +1, and this is going to be our negative axis, okay? So the level for 0 is positive and that for 1 is negative in NRZ-L. So suppose this is your data, which is 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1. All right, so how we are going to be encoding using NRZ-L is, for 0, we are going to be picking the positive. All right, and for 1, we are just going to be picking the negative. and this is going to go on for all of the bits. All right, so once again you have a 0, and this is just going to go on the positive. And then once again the 0 is going to go on the positive, then you have a 1 and that's going to go on the negative, and then you have a 1 that's going to go on the negative. You once again have a 0 that's going to go on the positive, positive, positive. Then once you have a 1 that's going to go on the negative, and then on the negative. Alright, so once again, be careful that each of these bits are of the same interval. So that's what the vertical axis over here are referring to. So let's say if for the first bit 1 second is allocated, then for the second bit you will also have 1 second allocated. Alright, and another thing is, see that the signal in nowhere does it touch the 0 axis, right? Because it does not return to 0. Okay, so that was the concept behind NRZ-L. In the second variation, NRZ-I, the I stands for invert. Alright, so now in this encoding, unlike NRZ-L, you don't have predefined levels for 0. Like in NRZ-L, I decided that 0's level would be positive and 1's level would be negative. Like this was decided for NRZ-L. But for NRZ-I, what I'm going to do is I'm going to see the change or the lack of change in the level of the voltage, and that is going to be determining the value of the bit. Now, if there is no change, then this means 0, and if there is an inversion, then that is 1. So let's see how this encoding works. Okay, so suppose you have 0, and 0 in NRZ-I means no change. So you can either start from the positive, or I'm just going to be marking this over here. This is going to be positive, this is 0, and this is negative. And this is my time axis. Alright, so once again you have bits assigned. Like this is the data that we are going to be encoding into the signal. Let me just change the color of the marker. Alright, so 0 means no change, right? So assuming that the previous level was in positive, then you start from here. Now you could also have started from the negative axis as well, because 0 means no change. So it could either be on the positive, it could either be on the negative. It really doesn't matter, right? Just to refer to the fact that it's not changing. All right, so now for when the duration of 0 is done, then you have 1, right? So 1 over here means inversion. So when you're trying to invert, that means that before you were in the positive level, now you're just going to be inverting that. So you're going to come to negative. All right, and then you're going to go on in the negative axis for the entire duration of 1. All right, once again, now you have 0. And since you have 0 over here, so it means no change. So since you were in the negative axis when 1 ended, so you're just going to be carrying on from here, and you're just going to stay in the negative axis. So once again, you have a 0, and 0 means no change. So you're just going to be carrying this on for the entire duration of this bit. And then you have a 1. 1 means inversion. So now you are in the negative axis, so you're just going to be inverting and going to the positive voltage. And then you're going to carry this on for this one. Once again, you have a 1, and 1 means inversion. So since you were in the positive, you're just going to come down to negative, and then you're going to carry this on for the whole duration for this bit. Once again, you have a 0, so you just carry on and not change the level, because 0 means no inversion and 1 means inversion. You just carry on the 0, and then once again you have a 0, so you just carry on, not change the level, and another 0, so you just carry on. And then you have 1, 1 means inversion, and now you're in the negative, so you're gonna go back and go to the positive, and then once again you have a 1, and right now you're in the positive axis, so you're gonna change and flip and invert that to negative. Alright, so another thing to notice here is if you had chosen the first level for 0 from the negative, then you would just get a complementary signal to this one, and that would have been correct as well. You could have just started from here, and if that was the case, then your one would flip over here and the entire signal would just be complementary to the one that I drew, and both of these are correct.